So up to this point, we've talked about vectors in two-dimensional space, and today we're going to talk about vectors in three space, or in three dimensions. You'll see I've got a couple of pictures drawn here on a 3D plane. We have an X, Y, and Z axis, and if you will, each of these vectors is popping out into space and has an X, Y, and Z coordinate to it. X always comes first, Y second, Z third. The magnitude of a three-dimensional vector, very similar to the magnitude of a two-dimensional vector, except we're not necessarily doing a Pythagorean calculation, but we're taking the square of each of the terms, adding them together, and taking the square root of it. So much like the two-dimensional vector, magnitude is calculated the same. So if we want to take and find a ordered triple that represents a vector, much like we did an ordered pair representing a vector, again we go tip minus tail for these two coordinate points. You'll notice once again that in this case I have 2 points notated by the parentheses rather than the vector, if you will, brackets. So if I want to find vector AC, I'm going to once again take tip minus tail, and I know that C is going to represent the tip, A is going to represent the tail. So I take 6 minus negative 1, 14 minus 2, and negative 2 minus 7 to get my vector representation of AC. That's going to give me 7, 12, and negative 9 respectively, and that's what we can call our vector. Like our two-dimensional vectors, we have these standard unit vectors in three space as well. I represents a x component of 1, J represents a y component of 1, and K represents a z component of 1 in our three-dimensional plane. So now, if we want to take and add the two vectors, very simply, we just add the components like we did in two-dimensional vectors. We're going to take this scalar of 4, multiply it by a vector x, and a scalar of negative 3, multiply by a vector y, and then add the two, and then at the end I'll just put it in unit vector form. So 4x is equivalent to 8, 48, and 0. Negative 3y is equivalent to 24, negative 12, and negative 21. When I add those, I get 32, I get 36, and negative 21, which would represent the sum. If I wanted to put that in unit vector form, I get 32i plus 36j minus 21k, and that would represent the sum. If I want to take and find a dot product of a three-dimensional, very similar dot product of a two-dimensional, take the product of the x's, product of the y's. The only new thing is we take the product of the z's, and then we add those three products together. And once again, if that dot product is equal to 0, then we know those vectors are perpendicular. So let's take and find A dot B given the two vectors A and B here. We take the product of the x components, 2 and 8, add that to the product of the y components, 3 and 3, and add that to the product of the z components, negative 4 and 2. Gives us 16, 9, and negative 8, which is a total of 17. These are not perpendicular. If we want to find a unit vector, We do that once again the same way we did it in 2-space. Take the vector components and divide each of those by the magnitude of the vector, and then say that is our unit vector pointing in the same direction as the original vector. So here I have a three-dimensional vector, 3i plus 4j minus 2k. I want to find the unit vector in the same direction as that vector. So in order to do that, I need to find its magnitude. Take 3 squared, 4 squared, and negative 2 squared. Add those all up and find their square root. That gives us the magnitude of v. So I've got 9, 16, and 4, which gives us the square root of 29. So if I want to find a unit vector here, I'm going to take the x component of 3, divide that by root 29, give that the I. 4, divide that by root 29, give that the j. And minus 2, divide that by root 29, and give that the k. And that's my unit vector pointing in the same direction as the original vector. Finally, we want to find the angle between those two vectors. Again, it's the same calculation as we had before in our two-dimensional case. We take the dot product of the two vectors divided by the product of the two magnitudes, and that's going to equal the cosine of the angle. So let's just go ahead and do that. Find the dot product first. Let's go u dot v, or u dot w in this case. So we have 1 times negative 3 for the x components. We're going to add that to negative 2 times 4 for the y components, and add that to 5 times 1 for the k components, or the z components. So I have negative 3 plus negative 8 plus 5, which in this case is going to be negative 6. Then I find the magnitude of each, so that's 1 plus 4 plus 25, all square rooted. That will give me the magnitude of v, which gives me a total of the square root of 30. Magnitude of w is going to be equal to 9 plus 16 plus 1 square rooted. Gives me a total of square root of 26. Going to find the cosine of the angle formed. Will give us negative 6 over square root of 30 times the square root of 26. Again, we'll take the inverse cosine, and that gives us roughly 102.4 degrees. Three-dimensional vectors, as you can see, are a lot like two-dimensional vectors. Really the same calculation, same quantities, except for the fact you've got the z-axis or the k term to deal with.